It's good to be with all of you once again. Today, we are going to talk about the cross product. The cross product and its uses. The cross product. In the previous section, we learned that the dot product of two vectors is a scalar. Here, we see that another way of multiplying vectors in 3 dimensions, let me underline that, this only works in 3 dimensions, is the cross product, and the result is a vector. For this reason, it is also called the vector product. So here's the definition. If A is the vector A1, A2, A3, and B is the vector B1, B2, B3, notice they're both in 3 dimensions, then the cross product of A and B is the vector A cross B equal to vector A2, B3 minus A3, B2, comma, A3, B1 minus A1, B3, comma, A1, B2 minus A2, B1, end of the vector. Whew, that's a lot. Good news, you don't need to memorize that. So note, the result of a cross product of 2 vectors is a vector perpendicular to both of the vectors you started with. As you can see, this relationship is not easy to remember, and so we will use the notation from matrices in linear algebra called the determinant. Interestingly enough, this is the second time we've used linear algebra style approaches in this class. We previously used them to solve systems of equations. Now we're using the determinant. So a determinant of order 2 is defined in this manner. So first, notice we notate it using these vertical bars, and you'll notice that there is no top or bottom on those vertical bars. They're just up and down, no side-to-side component. Okay, and the determinant is the 2x2 determinant, that would be 2 rows, 2 columns, is defined by the product of the entries on the diagonal, AD, and then we subtract the entries on the other diagonal, BC. So it's AD minus BC. So let's do an example of this. Example 1. Find the determinant of the matrix 0, 2, -5, -3. And so to do this, we're going to multiply the diagonal entries, and we get 0 times -3. And then we subtract the product of the other diagonal, which would be BC, so 2 times -5, and the product is 10. In linear algebra, we'll talk a little bit about what this 10 represents. For the time being, maybe I'll just kind of give you a sneak preview. This 10 would represent a scaling factor of a linear transformation. That's a linear algebra concept. It'll actually show up again in Calc 4 when you learn about the Jacobian. But for the most part, for us, it's just a tool for calculating. A determinant of order 3 can be defined in terms of second order determinants as follows. So we're going to take the entry A1 here, and we are going to multiply it by the determinant of the other rows and columns. If you will, take the A1 and then cross out everything else that's in that row and that column, and so multiply A1 by the determinant of the stuff that's left. And then we will subtract, and we move over to the A2. We cross out everything that's in the A2 row and A2 column and multiply by the determinant of the stuff that's left. and then we add. This goes plus, minus, plus, minus, plus, minus, et cetera, et cetera. We add, and we're focusing in on the A3 element. We cross off everything that's in the row with the A3 and the column with the A3 and multiply by the determinant of the stuff that's left. Okay. And each of those 2 by 2 determinants is calculated as we discussed previously. Let's do an example because this can look a little bit confusing, but it's actually pretty straightforward. Example 2. Let's find the determinant of the matrix 0, 2, 6, 4, negative 3, negative 1, negative 2, 1, 5. So to do this, we're going to expand across the first row. So we're going to take 0 and we're going to multiply it by what's left if we cross out everything that's in the row, same row as the 0 and the same column as the 0. We take all the stuff that's left and we put it inside the smaller determinant. Okay. Obviously 0 times anything is 0, but for the sake of completion, we'll write it down here. So then we keep going. That first sign was a plus. Our next sign is going to be minus, and we keep going across that top row. So minus 2. And then what are we going to multiply 2 by? Well, we cross off everything else in that top row with the 2, everything in the column with 2. And so we're going to multiply by a determinant made up of the stuff that's not crossed off. 4, negative 1, negative 2, and 5. Good. And then we're going to add. We keep moving across that top column. So notice we had the blue 0, the blue 2. Now we're going to have a blue 6. And we're going to multiply that blue 6 by a matrix, or by a determinant, I should say. And what is it the determinant of? Well, we cross off everything that's in the row with the 6 and the column with the 6. And we're left with just the entries 4, negative 3, negative 2, 1. And so notice that what we've done is we've taken that original 3 by 3 determinant and we've created a sum, so to speak, of 3 2 by 2 determinants. This is a recursive method. So it should be pretty clear that the first bit is going to be 0. Then we'll have minus 2 times 4 times 5 is 20. Minus, that minus is built into the formula. And then we have negative 2 times negative 1 is 2. Plus 6 times, so let me make sure your colors are here. So here's the 20, here's the 2. And the minus sign is just built into the formula for you. So now 4 times 1 is 4, minus, the negative is built into the formula. And then the product of the other diagonal entries, negative 2 times negative 3 is positive 6. 4, 6. And if we put all this stuff together, we have negative 2 times 18 plus 6 times negative 2, which looks like negative 36 plus negative 12, or negative 48. And again, you might ask, what does this number represent? This would represent the scaling factor of a linear transformation. All right, so let's connect our cross product, which is the concept we're learning about, with this little tool that we've learned called the determinant. So if I want to find the cross product of two vectors, A equal to A1, A2, A3, or A1I plus A2J plus A3K, and B equal to B1, B2, B3, or B1I plus B2J plus B3K, I can remember this cross product by writing it as follows. I could write A cross B equals, and then notice I'm going to take all of those A entries and put them in line 2 of the determinant, all the B entries and put them in line 3 of the determinant, and then in line 1 I'm going to put I, J, and K. So when I calculate this 3 by 3 determinant, notice I'm going to get an I tied to the first 2 by 2 determinant. There's a minus sign, it's just built into the formula, and then a J in front of tied to the second 2 by 2 determinant, and a K tied to the third 2 by 2 determinant. We can go through and calculate and rearrange these various determinants as follows. So we notice that the first determinant tied to the i's here is going to be A2 minus B3 minus A3 B2. And then the second one would be A1 B3 minus A3 B1. And the third would be A1 B2 minus A2 B1. And again, notice that there's this negative built into the formula. Okay. Well, having a negative built into a formula is a little bit awkward. So in the next line, I am going to reverse my order. Well, next line, I'm going to distribute that negative. So I have minus a plus, whereas above I had plus and minus. And then in the last line, I'm going to reverse the order. So notice that these two have swapped sides. And that's the same formula that we had for the cross product earlier. So rather than memorizing some ugly formula like this for your cross product, we'll just work with our determinant. It's just a much, much easier and more efficient way of remembering this formula. Example 3. Find the following if A equals 2I plus J plus K and B equals negative 4I plus 3J plus K. So I'm going to start by putting in my I's, J's, and K's at the top. And then the A vector will be 2, 1, 1. The B vector will be negative 4, 3, 1. So here's my cross product determinant. And so I will start by expanding around the I. And so how much I will I have? Well, I'll focus on everything that's left. So I have 1, 1, 3, 1 times I. And then there's a minus sign built into the formula. Now I expand around the J. So I have 2, 1, negative 4, 1 times J. And then plus. Lastly, I'll expand around the K. So if I expand around the K, then I will have the determinant of 2, 1, negative 4, 3 times K. Expanding this out, we'll have, in front of our I, we'll have 1 minus 3, or negative 2i, minus, this is the minus that's built into the formula, 2 minus 4, or 6, j, plus 6 minus 4, or 10, k. So A cross B in this case is negative 2i minus 6j plus 10k. So notice that in B, the only change is going to be that the orders of the second and third columns in our cross product are going to be reversed. So we need to calculate the cross product of I, j, k, and then we want to reverse the two rows. So negative 4, 3, 1, 2, 1, 1. And this cross product will be the i's times all that stuff. So that would be the determinant of 3, 1, 1, 1 times I. And next we focus in on the j's. Okay. So this would be a minus that's built into the formula. So I'll have negative 4, 1, 2, 1 times j plus and we're going to expand around the k. So we'll have negative 4, 3, 2, 1 times k. Oops, something like that. We can expand all this out, and we get 3 minus 1, or 2i, minus, this is the minus that's built into the formula, and then we have negative 4 times 1, or negative 4 minus 2, so we have minus 6j plus negative 4 minus 6, or minus 10, k. Simplifying, that would be 2i plus 6j minus 10k. And what I want to observe from this example is that these two results have the opposite sign. Up above you have negative, negative, positive. Below you have positive, positive, negative. So what do we observe from this example? We observe that A cross B is equal to negative B cross A. So this may be the first example that you had in your mathematical career where multiplication is not commutative, right? The order does matter in the multiplication. So let's use the definition of the cross product to show that V cross V is equal to the 0. This would be the 0 vector. So to do this, we can take V, cross it with V, and we don't know exactly what this V is, but we would write it as I, J, K, and then maybe V1, V2, V3, V1, V2, V3 for the entries. Notice we have the same entries in the second row and the third row because it's V cross itself. And so this would be equal to, when I expand across the I, we would get v2, v3, v2, v3 times I. And then we have the minus sign built into the formula. Expand across the J. And we have v1, v3, v1, v3. Plus, now we expand across the K. And v1, v2, v1, v2. Okay. At this stage, we need to actually calculate the 2 by 2 determinants. And so we have v2 times v3. Think about it, v2, v3 minus v2 times v3. Oh, that's a funny way of writing 0 in the first component. And then we have v1 times v3 minus v1 times v3. Again, that's a funny way of writing 0 in the Y or J position. And lastly, v1 times v2 minus v1 times v2. Again, 0 in the K or the Z position. And so we get that V cross V is equal to the 0 vector. Recall from the previous section that two vectors A and B are orthogonal. That would be perpendicular or normal if and only if A dot A is equal to 0. Here, this is the 0 scalar. We can show the following theorem. The vector A cross B is orthogonal to both A and B. And so this is a big deal. The cross product gives us a way of finding a vector orthogonal to A and B. Tool for creating a perpendicular vector. Let's look at a manipulate. So let's look at this animation to try to understand what's happening graphically with the cross product. So in this picture, we are starting with the vectors u and the vector v, and we're crossing them, and we're graphing u, v, and also that cross product u cross v, all on the same axes. And what I hope that you notice pretty quickly is that the cross product vector is perpendicular to the plane formed by kind of connecting the u and the v vectors together. Perpendicular. Notice that u and v are not perpendicular, but the u cross v vector, the green vector, is perpendicular to both u, the red vector, and also perpendicular to the blue vector. You might ask how big, like how long is that green vector? And the length of that green vector is given by this parallelogram. It corresponds to the area of this parallelogram here. And we'll talk more about that in the lesson. So the cross product is a vector perpendicular to the red vector and the blue vector, perpendicular, and the length of that vector is the same as the area of this parallelogram that's formed from the red and the blue vectors. So u cross v is orthogonal to u and to v, and in this particular case, the length of the green vector is 2, which corresponds to the area, that gray area in the picture. You might also notice that or think to yourself, there's actually two vectors that could be of length 2 that are perpendicular to the red and the blue vector. How do I know which one it is? And that involves using what we call the right-hand rule. Let me talk a little bit about the right-hand rule. I think I might be getting ahead of myself, but that's okay. So take your right hand, and in this case, you would take your pointer finger and point in the direction of the first vector listed. So maybe the U vector, so I was pointing to myself, and you'd let your middle finger or the rest of your fingers point in the direction of the second vector listed. So first vector, second vector, and then your thumb will go in the direction of the cross product itself. It says the cross product is pointing up. Once again, looking at it on the picture, if maybe I could rotate around a little bit. So notice that if my red vector is pointing kind of to the left and my blue vector is pointing out of the screen, then my thumb would be pointing up in the direction that I want. If I tried to reverse it, if I try to use my point in the direction of the blue one first, and then the red one second, it's going to force my hand to flip over, and your cross product would be pointing down. So first vector with your pointer finger, other vectors with the rest of your hand, thumb points in the direction of the cross product, whether that's up or down. Example 4, find a vector perpendicular to the plane that contains P, 1, -1, 0, Q, 2, 1, -1, and R, -1, 1, 2. So I have 3 points that are living in 3 dimensions, P, Q, and R, and they form some sort of a plane. And we're looking for a vector that is perpendicular to that plane. So if I want to find a vector that's perpendicular to that plane, then what I can do is I can take advantage of the fact that every time I see the word perpendicular, I think create perpendicular, I need a cross product. Get rid of perpendicular, I need a dot product. In this case, I want to find a perpendicular vector. So I need cross product. Well, in order to do the cross product, I need 2 vectors. Shouldn't be too difficult to see that we could look at those, the PQ vector and the PR vector. So PQ is equal to Q minus P. So that'd be 1, 1 minus -1, 2, -1 minus 0, and then what do I need? RP, or sorry, PR would be -1 minus 1, -2, 1 minus -1, 1 plus 1 or 2, and 2 minus 0, which would be 2. Let me just double check these for a second. 2 minus 1 is 1, 1 minus -1 is 2, and then -1 minus 1 is -2, 1 minus 1 is 2, 2 minus 0. Okay. And so if I want to find this perpendicular vector, then I would just look for the cross product of these 2 vectors. So PQ cross PR would be equal to I, J, K, 1, 2, -1, -2, 2, 2, which would be I times all that garbage, the determinant of all that garbage. So I have 2, -1, 2, 2 times I minus that's built into the formula. So we have the determinant of 1, -1, -2, and 2 times j. And then for k, we're going to multiply by the determinant of 1, 2, -2, 2 times k. All told, we have 4 minus 2 is 6, comma, don't forget this minus sign, but 2 minus 2, so 2 minus 2 would be 0, and I want a -0, which is still 0, and 2 plus 2 would be 4. And so this vector 6, 0, 4 would be perpendicular to the plane that contains the points P, Q, and R. There's an error here. So this is equal to 2 times 2 minus -2 or 6, comma, remember the minus sign built into the formula, but 2 minus minus 2 or 0. It could be negative, but that doesn't make a difference. And then 2 minus 4, which would be 6. And so this vector here would be perpendicular to the plane that contains P, Q, and R. We could check pretty quickly by dotting it with the vector PQ. So notice 1, 2, -1 dotted with 6, 0, 6 would be 0. And we could also dot it with the vector PR, -2, 2, 2. And that dot product would also be 0. That's our quick check to make sure that we did our cross product properly. As I mentioned earlier, that if A and B are represented by direct line segments with the same initial point, then the cross product A cross B points in a direction perpendicular to the plane through A and B. It turns out that the direction of A cross B is given by the right-hand rule. So if the fingers of your right hand curl in the direction of rotation, sorry, it's rotation, not ration, rotation, through an angle less than 180 degrees from A to B, then your thumb points in the direction of A cross B. Or if you point in the direction of A, point the rest of your hand in the direction of B, then your thumb will point in the direction of A cross B. Now that we know the direction of the vector A cross B, the remaining thing we need to complete its geometric description is its length, A cross B, magnitude. This is given by the following theorem. If theta is the angle between A and B, so that 0 is less than or equal to theta is less than or equal to pi, then the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of theta. One interesting and rarely useful result of this is that two non-zero vectors A and B are parallel if and only if A cross B equals 0. So a way of finding out if vectors are parallel is by taking their cross product. But there's other methods that are a little bit more valuable. We can also interpret that the length of the cross product A cross B is equal to the area of the parallelogram determined by A and B. So the area of the parallelogram here is equal to its base times its height. So its base is that A length, and then the height is B sine theta. So the area of the parallelogram would be equal to the magnitude of that cross product vector, just like we saw in the previous animation. Let's look at another animation that shows us a similar idea. All right, so here we want to better understand our cross product. So first of all, notice that the cross product, the green vector, is perpendicular to the red and also perpendicular to the blue. Okay, so that's good. Also, let's once again see our right-hand rule. So if I point in the direction of the A vector with my pointer finger, take the rest of my fingers and point in the direction of the blue vector, then my thumb is pointing up. Or another way of doing it, as we described in the notes, is put all of your fingers in the direction of the red vector, curl them around, sort of making a fist. So they're going towards the blue vector. And again, your thumb is pointing in the direction of the cross product. Okay. And we can tweak these vectors a little bit. So notice that if we adjust our red vector, then the green vector is also going to shift, so it stays perpendicular to both the red and the blue vector. Right? As these vectors change, the green will always be perpendicular. But notice also that the bigger the parallelogram that's formed by the red and the blue vector, the longer the green vector is. The length of this green cross product vector represents the area of that parallelogram that's formed by the U and the V, or the red and the blue vectors. Example 4 revisited. Find the area of a triangle with vertices P, 1, -1, 0, Q, 2, 1, -1, and R, -1, 1, 2. So this is the same situation we talked about earlier, but our question has changed. Now we are trying to find the area of a triangle. And so we have these 3 points, once again, P, Q, and R, and we recognize that they form a triangle, and we wanted to find, previously we found the vector that was perpendicular to P, Q, and R. This was our cross product. And to do that, we found the PQ vector and the PR vector. And using the PQ and the PR vector, we were able to find the red vector being PQ cross PR. And I think we found it to be 6, 0, 6. Now, graphically, we could ask, how long is that vector? And well, its length is the same as the length of a parallelogram formed by taking the PQ and the PR vectors. And so if we want to find the area of a triangle, we notice that the area of the triangle is exactly half the area of the parallelogram, and the area of the parallelogram is going to be the area of this red vector. So area of parallelogram equals the magnitude of 6, 0, 6. Should be square root of 36 plus 36, or 6 root 2. And then what we want is that area of the triangle. And so area of the triangle is half this, or 3 root 2. In the previous section, we introduced Hermann Grassmann as one of the founders of our modern vector analysis. In about 1840, Grassmann was already able to deal with the multiplication of vectors in 2- and 3-dimensional spaces. he defined the geometric product of two vectors to be the surface content of the parallelogram determined by these vectors. Think cross product. And the geometric product of three vectors, think scalar triple product that we will talk about shortly, to be the solid parallelepiped formed from them. Defining in an appropriate way the sign of such products, he was able to show that the geometric product of two vectors is distributive and anti-commutative. See the theorem below. And that the geometric product of three vectors all lying in the same plane is zero. There's a one-to-one correspondence between Grassmann's products and the modern cross product. The advantage of Grassmann's method is that, unlike the cross product, it is generalizable to higher dimensions. If we apply the concepts of the cross product to the standard basis vectors I, j, and k, using theta equal to pi over 2, we obtain the following. We obtain that I cross j is equal to k. We get that j cross k is equal to I, and we get that k cross I is equal to j. And I'm sort of orienting my hand in alignment with the standard arrangement of the axes. We get that j cross I is equal to negative k. We get that k cross j is equal to negative I. And we get that I cross k is equal to negative j. Notice again that I cross j does not equal j cross I. Thus, the cross product is not commutative. Also, I cross j is the same as I cross k or negative j, whereas I cross j is 0 cross j or 0. Right? So you don't even have the associativity of vectors that we're used to. Here, I and j are associated. Here, I and I are associated, and yet, red warning, negative j is not the same as I. All we were doing was switching the association. So the associative law for multiplication does not hold generally. That is, A cross B cross C is not generally equal to A cross B cross C. However, some of the usual laws of algebra do hold for cross products. The following theorem summarizes the properties of vector products. So theorem, if A, B, and C are vectors, and little c is a scalar, then A cross B equals negative B cross A. CA cross B is equal to C times A cross B is equal to A cross CB. So notice in this particular case, the C is a scalar. A cross B plus C is A cross B plus A cross C. So you can distribute across with addition. In 4, A plus B cross C is equal to A cross C plus B cross C. And so you can distribute with addition whether the addition is at the front end or the back end of the product. A dot B cross C is equal to A cross B dot C. So the dot product is a happy thing. And then the strange formula, A cross B cross C is A dot C times B minus A dot B times C. It's this sixth one is the strange formula. Here, what's important is that you remember that the cross product has strange behavior. Behaves strangely. So if you can remember that it behaves strangely, then you will remember to look these things up when you come across these types of formulas. I would say that these formulas do not come up often enough in this class to make them worth memorizing, provided that you remember that the cross product just has kind of strange behavior and that you have to double check anytime you start using cross product type properties. This next section is interesting because it gives us a little bit of a connection to 3D geometry. So this is the scalar triple product. The product A dot B cross C is called the scalar triple product. It's calculated using the determinant below. please note that this quantity can be positive, negative, or zero. So it's A dot B cross C equals, and then all we're taking here is a determinant, ordinary determinant of A, B, and C. Notice there's no I, J, and K in that top place. Why would that be? That would be because when you find the cross product, that would give you the B and C rows with I, J's, and K's, and then we would multiply by A, and so the first component would multiply by the I stuff in B cross C, the second component of A would multiply by the J stuff in B cross C, the third component of A would multiply by the K stuff in B cross C. And so the A1, A2, and A3s are sort of taking the place of the I's, J's, and K's in that cross product. You can work it out if you want to see it more clearly. But what we're really interested in here is the geometric interpretation. So the geometric significance of the scalar triple product can be seen by considering the parallel piped determined by the vectors A, B, and C. Let's see if you can see it. So here's our A vector. Here's our B vector. And then our C vector is the one that's going into the board. And so the three of those are going to form a parallel piped. Think like a three-dimensional parallelogram, if you will. So the area of the base of the parallelogram is given by B cross C. So that would be B cross C, B cross C, and specifically its magnitude. And if theta is the angle between A and B and C, then the height h of the parallel piped is the magnitude of A times the cosine of theta. Wait, cosine because reminds us of that dot product. Also, we're using the magnitude of cosine here instead of just cosine theta because we want to make sure that our height is going to be positive. So therefore, the volume of the parallel piped is V equal to area of the base times the height, or the magnitude of B cross C times the magnitude of A times the magnitude of the cosine of theta, or the absolute value of A dot B cross C. Just a note here. These are absolute values. Not magnitudes like you've seen them in the past, because remember, the dot product's always going to give you a scalar. So thus, we have proved the following theorem. The volume of the parallel piped determined by the vectors A, B, and C is the magnitude of their scalar triple product, V equal to magnitude of A dot B cross C. Note, the parallel piped volume is 0 when the vectors are coplanar. And again, another way of thinking about this quantity is this is telling us something about a scaling factor, telling us something about a scaling factor of a linear transformation. I say that because you have this 3D determinant. Which is kind of cool. So those are just sneak peeks that'll give you a hint into linear algebra and a hint into Jacobians when you see those in Calc 4. Example 6. Find the volume of the box, the parallel piped, determined by A, B, and C, where A is 1, 2, -1, B is -2, 0, 3, and C is 0, 7, -4. Well, the nice part is that this volume will be equal to the absolute value of whatever our determinant is. So we've got 1, 2, -1, -2, 0, 3, 0, 7, -4. So we'll take 1 and multiply it by 0, 3, 7, -4. Subtract, remember that negative is built into the formula. So now we're moving across, so we hit the 2. We multiplied by the determinant of -2, 3, 0, -4. And then we add -1 times the determinant of -2, 0, 0, 7, which is a funny way of writing 1 times -21 minus 2 times 8 minus 1 times -14, which would be -2. I think I've got -23. And notice this is a negative, but we want a volume. And so what we need is we need the absolute value of this quantity. Or positive 23. It's the absolute value. Since we're talking about volume. Torque. When we turn a bolt by applying a force F to a wrench, we produce a torque that causes the bolt to rotate. The torque vector points in the direction of the axis of the bolt according to the right-hand rule. The magnitude of the torque depends on how far out on the wrench the force is applied and on how much of the force is perpendicular to the wrench at the point of application. The number we use to measure the torque's magnitude is the product of the length of the lever arm R and the scalar component of F perpendicular to R. So the torque vector, that's that funky T, is equal to R cross F. And the magnitude of the torque vector is magnitude of the torque vector equal to the magnitude of R cross F, or magnitude of R times magnitude of F times the sine of theta. For those of you that have used wrenches or screwdrivers or what have you, this should make sense. The longer the wrench, the greater the leverage that you have, or the greater the torque that you have on the bolt that you're trying to unscrew or tighten. Let's look at a manipulate. Okay, in this picture, notice that the R, the red R, is representing the wrench, if you will. So this represents the wrench, and the F represents kind of the direction that you're pushing the wrench. So you're pushing the wrench, and the torque is saying how much torque, how much twisting power, if you will, is there on the bolt that you're trying to twist. Notice that when you are pushing at when the force is at a 90-degree angle from the wrench, then you're going to have maximum torque. If you, let's see if let me go the other direction. It won't let me go the other direction. If your force went the other direction, then the torque would reverse. And so that sort of turning force, if you will, that torque would be in the opposite direction. Think lefty-loosey, righty-tighty. Longer wrenches, greater torque. Smaller wrenches, smaller torque. Greater force, greater torque. Smaller force, smaller torque. Angles that are either kind of back towards the bolt, if you will, or away from the bolt are going to generate a lot less torque. So if you want to get that maximum torque, you'd want to be pretty close to perpendicular to kind of that handle of the wrench. Example 7. Find the magnitude of the torque generated by applying a 20-pound force to a 3-foot bar, creating a 70-degree angle. This is actually kind of a funny example because a 20-pound force is not a lot of force. 3-pound bar is a pretty long bar, but let's see how it all comes together. So we have this bar that's 3 feet long. And then we have a force that's being applied at 70 degrees. So maybe here's that 70 degrees. So your force is going to be 20 pounds. And so if we want to find the torque, then at least the magnitude of the torque, we're not actually worried about the torque vector itself. So the magnitude of the torque vector will equal the magnitude of the wrench, the distance, times the magnitude of the force, times the sine of, in our case, 70 degrees. Where we have 3 times 20 times the sine of 70, which, according to my Texan friend, is 3 times 20 times the sine of 70 degrees, making sure I'm in degree. I'm in degree mode. 60 something's funny. Oh, 3 times 20 times the sine of 70. I've got 56.4. 56.4, and I believe these are foot-pounds. Foot-pounds of torque. For those of you that work on cars, you might recognize torque by a torque wrench, right? And a torque wrench says it will let you crank on a bolt, but give it exactly the right amount of torque by saying it won't let you, it'll sort of release if you go too far. And so you would set it at 40 foot-pounds or 60 foot-pounds or something along those lines. Those of us that don't own torque wrenches try to be careful and get things tight enough, but not snap our bolts inside our cars. So there you are. There's the basics of the cross product. As you can see, it's a little bit of a nuisance to calculate because of the determinant that you have to use, but otherwise is actually pretty straightforward. So basically, the cross product gives you perpendicular vectors. Its magnitude includes a sine function, whereas the dot products uses a cosine function. We know we can remember that the dot product has a cosine because the dot product eats perpendicular vectors for lunch. Cosine of 90 degrees or cosine of pi over 2 is 0. So thanks very much, and I look forward to joining you again for the next lesson.